Human fingerprints are detailed, nearly unique, difficult to alter, and durable over the life of an individual, making them suitable as long-term markers of human identity. Fingerprints may be used by police or other authorities to identify individuals who wish to conceal their identity or to identify people who are incapacitated or deceased and unable to identify themselves. Elements have a fingerprint equivalent. Since they are capable of absorbing and emitting light, every element has its own characteristic spectra. Just like crime scene forensic investigators, chemists use atomic spectroscopy to do basic analysis of many types of chemical materials. Spectroscopy is the branch of science that investigates and measures the spectra produced when matter interacts with or emits electromagnetic radiation. Scientists use a spectroscope, which is an instrument that uses a prism to divide light into its subcomponents. These investigations make use of the wave and particle character of light, and scientists witness a number of lines of various colors displayed. Those different color lines make up a line spectrum for an element. A beam of light is electromagnetic radiation emitted from a transmission source. We can envision light moving in a wave pattern like this sine wave. When it comes to measuring a light wave, generally the wavelength and frequency are considered. Waves are repeating patterns, and the wavelength is the distance from the peak of one wave to the peak of the next wave. Wavelength is represented by the Greek symbol lambda. The frequency is the measurement of the number of waves that pass a point in space each second. Frequency is represented by the Greek symbol nu, and it is commonly given hertz as the unit. Wavelengths are usually measured in nanometers, with the visible light spectrum ranging from about 700 nanometers on the longest waves up to about 400 nanometers on the shortest waves. The speed or velocity of light is calculated by multiplying the wavelength and the frequency. As you can see from this equation, wavelength and frequency have an inverse relationship. The shorter the wavelength, waves will pass more frequently through a point in space each second. Even though light's movement is somewhat different for every environment, we generally consider the speed of light to be 3.0 times 10 to the 8th meters per second. Max Planck is credited with discovery that when a light source gives out energy, it loses this energy in invisible packets called quanta. Albert Einstein identified that this energy was converted into separate packets of energy called photons, which carry the energy of light and other magnetic radiation. Photons are referred to as the particles of light. The amount of energy contained within a photon is proportional to its frequency. The energy of a photon is given by the equation E equals h times nu, where E is energy, h is Planck's constant, and nu is the frequency. This equation tells us that as the frequency of radiation increases, the photon energy increases. Planck's constant is the universal proportionality constant, and it is numerically represented as 6.626 times 10 to the negative 34 joules seconds. Early ideas about atoms had electrons moving around the nucleus without any consideration for specific patterns of movement. Instead, electrons were believed to have moved around randomly. As the field of chemistry evolved, more was learned about atoms, and it didn't take long for scientists to agree that this early concept of the atom was flawed. Today, there are two atomic models that are used. The first of these is Bohr's atomic model, and the second is the quantum mechanical model. In 1913, Niels Bohr introduced a model of a hydrogen atom that changed the way chemists thought about atomic structure at that time by explaining how the line spectrum was produced. His model depicted the hydrogen atom with a small, positively charged nucleus that was surrounded by an electron. The electron moved in a circular path or orbit around the nucleus, just like the movement of planets around the sun. These orbits were also referred to as energy levels, or shells. Bohr theorized that there was an electrostatic force between the positively charged nucleus and negatively charged electron, and it is this force that provides the centripetal force to keep the electron moving along its circular path and on its energy level. Bohr's model demonstrates that the energy of the atom is the sum of the potential energy of the electrostatic force between the nucleus and the electron and the kinetic energy of the movement of the electron. Bohr proposed that only certain stable orbits are allowed, those for which the angular momentum of the electron is an integer times the constant h over 2 pi. H is Planck's constant. The energy level or shell that an electron typically occupies is called its ground state, and the closer an electron is to the nucleus, the less energy it needs. This is in contrast to electrons that are further away from the nucleus that require more energy to get it into an excited state. Electrons can move from one stable orbit to another by absorbing or releasing an amount of energy exactly equal to the difference between the energies of the two orbits. Electrons can jump to higher energy levels when they absorb energy, and again, this is referred to as the excited state. Electrons can fall back to their original orbit. If an electron absorbs or emits light energy, a single photon of absorbed or emitted light must account for the required energy difference, as h times nu equals delta E. Delta E is the energy difference between the final and initial orbits. Sometimes the energy released by electrons occupies segments of the electromagnetic spectrum that human beings can detect with their naked eye. Little variations in the amounts of energy are seen as color differences. Bohr also theorized that the different energy levels were capable of holding different numbers of electrons. For example, the first energy level can hold a maximum of 2 electrons, while the second energy level can hold up to 8 electrons. Bohr's theory and atomic model really only apply to hydrogen atoms because of their atomic simplicity. However, his atomic model makes for a great introduction into the movement of electrons around the nucleus of an atom.